Hi everyone, this is the video lecture of Calculus 3, Math 2533, Section 12.4, double integral in polar coordinates. So let's think about double integral over this kind of region. That is, in polar coordinate, r is between 1 and 2, right? This is circle with radius 1, circle with radius 4, from 0 to pi theta. Now, if you try to do this one in xy coordinate system, you have to write it as a type 1. So, but then for this region and this region, your lower curve has a different function. This is y equals 0, this is y equals square root of 1 minus x squared. So you have to split into 3 different regions, as it is well written in the lecture notes, right? So you will have to do 3 different integrals. But in polar coordinate, that region is this rectangular one. If you draw this one in r theta, imaginary plane, not imaginary, it's an abstract plane where r and theta behaves just like x and y, rather than angle and the distance, that will be rectangular ones, right? So this kind of region is polar rectangle. When the corresponding region in r theta plane is rectangle, then we call it polar rectangle. So we want to find a way to calculate double integral over a nice region in polar rectangle in polar coordinates, not xy coordinates. So let's say you're given general polar rectangle. From A to B, R is from R equals A circle to R equals B, radius B, from here to here. Theta is from alpha to beta, all right? So this is polar rectangle. Now, the double integral, the basic idea of the double integral is the limit of Riemann sum. Riemann sum is obtained by taking your region into fine grids. And area of the small subregion, area times function value there. And you do the same thing for all small subregions. Add them up and take the limit as this delta x infinity goes to 0, or n and n go to infinity. So we do the same idea here. We split the whole polar rectangle using uniform partition of the angles. That is, do delta theta equals beta minus alpha over n, right? And theta j equals alpha plus j times delta theta. So this is theta 0. This is theta equals theta 1. Theta equals theta 2. All rate, let's say, theta j minus 1, theta j. And this is theta equals theta n. And also, we divide r uniformly. Delta r equals b minus a over m. Ri equals, starting from a, I times delta r. And okay, so like a uniform difference in length. Okay, so we want to think about theta I minus 1 to theta I. So this one, so-called Ij, okay? And then you choose a sample point here. Rij star, theta ij star. Okay? Then, first of all, so we have to do this. What's the area of the ij polar subrectangle? Aij. Think about it. This is, if you think about it, this is delta theta. All right? When delta theta is really, really small, then this length is r I delta theta. This is r I minus 1 delta theta. This is delta r. When delta theta is really small, and delta is also really small, this is almost a rectangle. So this area will be almost, I got this one from here. You remember theta, s, and r. Arc length s is r theta, when theta in radian. So this is ri minus 1. So ri minus 1 times angle delta theta. This is ri times delta theta, right? So this will be ri times delta theta delta r, right? Delta r, ri and ri minus 1 is almost the same. So I can use this one as a length and width, all right? So you have to do this. Function value at here, xij star, yij star times delta area of this. Okay. This is in polar coordinate, but in xy coordinate it has to be xij star, yij star. See? So just like the original double integral, function value times the area of that subregion. You have to add them up. 1 and I1 through n. M. And you take the limit. M and n both infinity. This is what we call double integral, right? Delta Aij is Ri delta theta delta r. So double integral over that. So this, you have this one, okay? Now, this one, so let's say your function f is given as a function of x and y. But your x coordinate is what? Rij star cos, r cosine theta, isn't it? Right? And y coordinate is r sine theta. Alright? The corresponding values. And delta, this one is r. Okay, so r ij star. Okay, we have to use ij star. We're going to use value at rij. Okay. And delta r delta theta. So when you look at this, this is some function of r and theta, isn't it? Right? Some function of r and theta, delta r, delta theta. All right? So it's just like integrating over r and theta region, like this. R from A to B, alpha, beta. So if I call it D, this is just like a double integral over this D in the corresponding r theta plane of this function, f of r cosine theta, r sine theta, times r dA, right? and D is in the r theta plane. Okay? Okay? And that is, you can then iterate integral, right? Because it's a rectangle in the r theta plane, right? So, dr d theta. Okay? So, double integral of f of x y in the region R in the xy plane is same as double integral of this new function of r theta going through this, right? Don't forget this r. xy change it to r theta. X equals r cosine theta, y equals r sin. Not only that, you have to have extra r. The new functions double integral over this rectangle in r theta plane, r theta double integral. Okay? When your domain is like polar rectangle, this, that can be a lot of times much easier than the double integration in xy plane. So, let's take a look at it. So I'm going to just write it here. So if your R is A to D for R, alpha to beta for theta, R f of x, y, d, A equals A to D, theta, f of r cosine theta, r sine theta, r dr d theta. This is what we just got. Okay? Then let's do example 1. Evaluate r, xy. Your r is what? Your r is x, y, both are non-negative. And then between the circle with radius 1 and 2, right? So the region is between 1 and 2. This is the region. That is a nice polar rectangle, right? R theta. R is between 1 and 2. Theta is between 0 to pi over 2, isn't it? Right? Then your integral I'm going to call I. Using this, 1 to 2 for R. 1 to 2 for R. Alright? 0 to pi over 2 for theta. dr d theta. Don't forget r dr d theta. And then what this means is that in the expression of f of xy, every x should be replaced with r cosine theta, and every y should be replaced with r sine theta. R cosine theta. Okay? So you have, now this is a separable, right, in double integral. So you can do separated r cubed dr. Remember in 12.2? In integrated integral, if your function is separable, you can actually separate your integral like this. Sine theta. Okay? And this one is easy. This is 1/4 r to the 4th, 1 to 2 times, if you call it u, this is du, isn't it? 1/2 of u squared, 1/2 of sine squared. Okay? Then 1/8, this one is 16 minus 1, so 15. This is 1 already. Then 1 minus 0. 15 over 8. Okay? So, this was particularly easier because your equation is your integral was separable. Okay, let me check the recording. Alright. Now, what if your domain is not exactly polar rectangle, but something like this? This is so-called type 2 in our data. That is, theta runs from alpha data there is a curve, not necessarily circle. Okay, this is r equals h2 theta. This is r equals h1 theta. So the polar curve, right? R equals some function of theta. You learned those kind of curves before, all right? Appendix H in calculus 2. Now, this is the domain D. You can describe D just like a type 2 in XY case. Theta runs from alpha to beta. Okay? So this is theta equals alpha, beginning angle of theta, and this is ending angle of theta. So theta from alpha to beta, and given theta, your R, see, for a given theta, your R, this is given theta. For given theta, R runs from here to here, isn't it? Right? Theta now if you think R is the first variable like X in XY, and theta is the second variable like Y in XY system, Y from somewhere to somewhere, for given Y, X runs from something about Y, something about Y. That is type 2. That's why I call that this is so-called type 2 in polar coordinates. In polar coordinates, we don't consider type 1. R, it is not just what we actually do here, all right? We only consider this case. In that case, in this kind of domain, generalized polar rectangle, not polar rectangle, type 2 polar region, then you just follow the same thing. Alpha beta for d theta. For given R runs from h1 of theta to h2 of theta, f of r cosine theta, r sine theta, r dr. Okay? So instead of alpha beta, you have, instead of theta, I'm sorry, this is alpha beta. This is A, sorry about that. Okay? Instead of AB, you have this. That's the difference. This, if F1, H1 theta and H2 theta are constants, then you get this. Constant R value means circle. This is not circle, general polar curve. Okay? So, example 2. Example 2. Find the volume of the solid lies under the cone. Right? Lies under the cone. Lies under the cone. above the xy plane and inside the cylinder, x squared plus y squared equals 2x. You know what? X squared plus y squared equals 2x means that x squared minus 2x, y squared equals 0, right? Adding 1, x minus 1 squared, y squared equals 1 squared. It's a circle with radius 1, center 1, 0. Okay, along x. So your circle is like this over here. See? And the cylinder is under, I don't know how to draw this. Okay? So you have an x, y, and z. Okay? You have a cylinder going up. It's top off here, and you try to draw a cylinder going through the origin and centered at 1, 0, going to 2, 0. So you have a cylinder, but then you have to carve out cylindrical. All right? That's the region we're talking about. So, actually, you have a nice picture in figure 9. See, page 856. Okay? There's a cylinder, and then there is a, this one cutting through. There's a cylinder was cutting through. Okay? And the cylindrical blade is take off. Okay? That's what you see. All right? Here, the difference is that your textbook uses your paraboloid. Here, cylindrical cut. That's the difference. Anyway, so now this one. So the volume of the solid. This one is z equals square root of x squared plus y. Volume of this solid under this graph over this region means that the volume is just the integral over d of upper surface function, right? This is the volume, right? Now we want to write this one in polar coordinate. First of all, in polar coordinate, r squared to x equals r cosine theta, right? X equals r cosine theta, y equals r sine theta, conversion from r theta to xy. Now, r cancel, r equals 2 cosine theta. This is actually r equals 2 cosine theta. And theta from minus pi over 2 to pi over 2. As theta increases, what is it? Your r is from 0 to this one, right? Always starting from the origin. So your domain d can be written as in polar coordinate. Theta runs from minus pi over 2 to pi over 2. And r always runs from 0 to this one. This is your f, h2 of theta. Okay? 2 cosine theta. That would be type 2 polar region. So, your integral volume can be written as just like that. There. Theta runs minus pi over 2 to pi over 2. 0 to 2 cosine theta in terms of r and theta. This is r, isn't it? Right? R squared cosine squared theta plus r squared sine squared theta is r squared plus parenthesis cosine squared plus sine squared theta equals 1. Square root of r squared is r. And then another extra r. dr, d. Remember, there is always extra r. when you change rectangular coordinate to polar coordinate. Okay? Then after that, it's easy. R squared 1/3 R squared R to the third from 0 to 2 cosine theta d theta. 2 to the third is 8. 8 over 3 cosine to the third theta d theta. Okay? And then you learn the techniques of integration. When you have odd power, you want to write it cosine square theta times cosine theta. And then that cosine square theta, 1 can be written as 1 minus sine squared theta, and then cosine theta d theta. Always separate one, and then leaving even power, and then using cosine squared equals 1 minus sine squared. And then we use u equals sine theta, give you du equals cosine theta d theta. And theta is between minus pi over 2 to pi over 2, give you u runs from minus 1 to 1, right? This is minus 1 to 1, 1 minus u squared and du. And this is very simple calculation. You can finish, all right? I did it slightly different way, but you can do the same way. You can do it this way. Either way, same thing. So you have 32 9 over 2. All right? So the most important step is getting this iterated integral in R there for type 2 polar region. Okay? I think I'm going to change Now, next topic, next one is example 3 on page 856 is almost the same as this. The only difference is here, instead of square root of x squared plus y squared, you have x squared plus y squared. Instead of r, you will have r squared. That's the only difference. Okay? Now, so in example, example 3, which is same as example 3 on page 856, instead of this, you will have paraboloid, right? Paraboloid cut on the top. Then everything is same, except that you will have top function, top surface function. Same region, this is r squared. R to the third, so 4, r to the fourth. 16, so 4. Cosine to the fourth power. Okay? So when you have, this is the technique you learn in calculus 2. When you have an even power, then you have to do what? Okay? Minus pi over 2 to pi over 2. You have to write a cosine squared theta, cosine squared and squared. Cosine squared is 1 plus cosine of 2 theta over 2. All right? So you have to use power reduction formula, which is in the variant of doubling the formula. And that in turn, square, so 4 here, 1 plus 2 cosine of 2 theta, cosine square of 2 theta. 4 cancel. And then 1 plus 2 cosine of 2 theta. And this one, again, another power reduction formula. Instead of theta, you have 2 theta. 1 plus double angle, which is 4 theta in this case, over 2. So then after that, you will just finish this calculation. All right? So then you can get the value you're looking for. Okay? You can see the notes and also in the textbook. All right? All right. Okay. Now in your textbook, they change it to this one as twice. Instead, you're doing from 0 to, because it's even function. You can do it instead from minus a to a, 0 to a and twice. That's what 4 to a. That's what they did in your textbook. Anyway, same thing. Okay? All right. The last example is example 4. Evaluate the iterated integral from 0 to 1 minus square root of 2 minus y squared minus y x squared y dx dy. Okay? Now, I'm going to call it. I want to write this one as double integral. And then want to describe d, where d equals. This iterated integral means that y runs from 0 to 1. For given y, x runs from this to this. And I want to analyze this. So first of all, y from 0 to 1. For given y, x equals minus this. What does it mean? What kind of curve is this? Square both. Hey, it's a circle. Circle with radius square root of 2. X minus means left semicircle, isn't it? Right? So left semicircle. So it is 1, right? For given y, when y equals 1, you get x equals negative 1, right? So it is part of left semicircle. Okay? Part of left semicircle. So for given y, left semicircle 2, and then another one is x equals negative y equals negative x. Going through this one. Right? They happen to be negative 1 and 1, both. Right? So from here to here. That's the region, right? Hey, this is a sector, isn't it? All right? Because that left-hand side part is a circle, right? It's a It's a circle. All right, right hand side is y equals negative x. Okay, this is domain D. So your domain D in polar coordinate, you can write it one. Your r, or theta, runs from minus pi. Here, I'm sorry. 3 pi over 4 to pi, isn't it? 3 pi over 4 to pi. Theta runs. And r runs from 0 to 2. 0 to square root of 2. Sorry. Radius to square root of 2. It's a polar rectangle, isn't it? When you have polar rectangle, then your integral will be r theta runs from 3 pi over 4 to pi d theta. And this one going from r from 0 to square root of 2. And x squared, r cosine theta squared, y, see, x squared, and y equals r sine theta, and then r dr d theta. Okay? So in the end, you're going to get what? R to the fourth, sine theta, cosine theta, isn't it? Okay? So this is again another separable function, right? Separable through multiplication. So r integral and theta integral. That one is u equals sine theta. We'll give you du equals cosine theta d theta. U du equals 1/2 of u squared, 1/2 of sine squared theta. All right. Wait a second. I'm so sorry. No, I'm sorry. This one's cosine squared theta sine theta. What am I doing? Cosine squared theta sine theta. So I have to do cosine squared theta and then sine theta d theta. So u equals cosine theta means du equals minus sine theta d theta. Sine theta is minus d minus u squared, right? So minus 1/3 of cosine to the third power. Okay? And this one is 1/5 r to the fifth. From 0 to square root. Okay? Then you can finish. Alright? So minus 15, 1/15. 2 to the 1/2, 2 to the 5/2. Alright? And cosine of pi is -1. -1 to the third power is -1. Minus of cosine 3 pi over 4 is minus 1/square root of 2 to the third power. Okay? So this is 32/square root of 2, right? 16, so 4/square root of 2. So I'm going to cancel minus. So you get 1/15, 1/15, 4/square root of 2, 1 minus this. Okay? So this is what? 1/15, 4/square root of 2, and this is 1 minus square root of 2/4. So distribute. 4 square root of 2. 4 cancel. Minus 2, isn't it? Okay? That's the answer. All right. So, in the end, this is all we use, right? When your region is very natural for polar, sometimes your integral is very natural in polar coordinates, but at least either function or domain is very natural in polar coordinates, either polar rectangle or type 2 polar region. Then polar rectangle, you do it this way. Type 2 polar region, do it this way. It's a type 2, right? You just describe your domain and set up the trade integral accordingly. That's all. And after that, calculus to integration techniques. All coming back to Honshu. All right? So, the most important techniques we mentioned is when you have an r cosine to the third theta. R power, you have to separate one cosine theta, and cosine squared theta should be written as 1 minus sine squared theta, and use u equals sine theta. And cosine theta theta will be du. When you have R even power, then you have to use power reduction formula. Cosine theta squared theta equals 1 plus cosine 2 theta over 2. Sine squared theta equals 1 minus cosine 2 theta over 2. Those two formulas are necessary. Okay, so that's the end of section 12.4. So it is supposed to be done in the first part of the week of Monday, March 30th. Okay? During the second part of the week, you have to do section 12.6 and 12.7 in the first part, first half of 12.7. Okay, I'm going to upload the video either Thursday, no later than Friday. Okay? We don't cover 12.5. So we finished 12.4. The next lesson is 12.6. Okay? Well, thank you and see you next time.